Dear students, my name is Dr. Amir Fawaz and in this video we will talk about reactions of pyridine. In our previous video we talked about the synthesis of pyridine, and here we will see the reactions. First we see the resonance contributing structures of pyridine. First structure would be this one. Then we have this one. And this one. So we can see here that position 2, position 4 and position 6, they are with lowest pi electron density. Thus they are more susceptible to nucleophilic substitution reactions, and for electrophilic substitution reaction we can see a general reaction with pyridine using an electrophile, and if C2 attack takes place we will get electrophile added on position 2, and in this case nitrogen would get positive charge. So this sigma complex is with nitrogen having positive charge. If attack is on C3, in this case we will have positive charge on C2, and in case of attack at C4 we will have again positive charge on nitrogen. So only this sigma complex is without N+. Therefore nitrogen, because is electronegative atom, carbon 2 attack and carbon 4 attack is not favorable, only carbon 3 attack is favorable, and after removal of proton we will get 3 substituted pyridine. So these were few general concepts by which we can understand the reaction of electrophile or nucleophile with pyridine and type of product or radiomeric product which has to be formed. Now we see the reactions. Because pyridine has lone pair on nitrogen, therefore electrophilic substitution reaction can also take place on nitrogen. So first we see electrophilic substitution reactions on nitrogen. If we treat pyridine with any Lewis acid, for example we call it L, and this Lewis acid can be aluminium chloride or antimony chloride, and as a result of this reaction a stable adduct is formed. If we react pyridine with a bronzed acid HX, protonation takes place at nitrogen, and this salt is formed. Similarly, pyridine can react with alkyl halides, and via substitution reaction we will get this compound, and reaction with acid halides can also take place, and as a result of these reactions an acylation can occur. So nitrogen would have positive charge and halide would surround the positive charge. If we have an alpha beta unsaturated compound attached to electron withdrawing group, it can be electron withdrawing group can be cyano group, any carbonyl for example. In the presence of halo acid, Michael addition can take place. And we get this product. Reaction with aryl halides can also occur, and we will get this type of compound after the reaction. Here L will have negative charge because it was neutral here, and after the donation of two electrons or one electron pair to Lewis acid, we will get negative charge on L. And next reaction here is, if we treat pyridine with peracid, we will get N oxides or pyridine oxides. So these were reactions of pyridine on nitrogen, and a related reaction is King-Ortoliva reaction. King-Ortoliva reaction. In this reaction, a ketone such as acetophenone or any active methylene compound can be used and reacted with pyridine in the presence of iodine, and as a result of this reaction we get this type of compound. This is possibly formed because first alpha iodination takes place here, and then pyridine replaces the iodine, and as a result we get this compound. Now we see further reactions of pyridine, electrophilic substitution reactions. In general, pyridine is more susceptible to SNAR reaction, nucleophilic aromatic substitution reaction, as compared to aromatic electrophilic substitution reactions. So first reaction is nitration. In general, nitration can take place in the presence of nitric acid and sulfuric acid, and this reaction requires high temperature, for example 300 degrees centigrade, and generally it is also low yielding, and only 15% of product is formed under these harsh conditions. However, if we use dinitrogen pentoxide for nitration, 3-nitropyridine is formed. So N2O5, and we get 3-nitropyridine. and this reaction can take place using N2O5 in nitromethane or SO2, and we present a mechanism with N2O5 using SO2 or HSO3 negative. In the first step this is formed, and then HSO3 negative attacks here at this position, and we get this. In the next step, NO2 rearranges and is attached on 3 position, and in the final step H2SO3 is eliminated to form 3-nitropyridine, and with this method approximately 70% yield of 3-nitropyridine is obtained. Next reaction is sulfonation, and in this case different reagents can be used to form sulfonic acid derivatives of pyridine. For example, if we treat it with oleum in the presence of HgSO4 at 250 degrees centigrade, we get 3 sulfonic acid derivative, and it can be converted at 360 degrees centigrade to 4 sulfonic acid derivative, which shows that this reaction is thermodynamically controlled, and this can also be formed directly from pyridine at 360 degrees centigrade. The use of Hg2 is to make sure that no protonation at nitrogen takes place or it is suppressed, and it coordinates with nitrogen, thereby allowing the oleum to form 3 sulfonic acid derivative of pyridine. If oleum is treated with 2,6-lutidine, which is a pyridine derivative, and it is reacted with oleum, we get this complex. Similarly, if we use 2,6-diterbutyl pyridine and allow it to react with sulfur trioxide at -10 degrees centigrade, we get substitution at 3 position, and if this pyridine derivative is reacted with oleum at 250 degrees centigrade, we get this derivative, and alongside that a sulfone derivative also. So this is sulfonation, and now we see halogenation reaction. As we can see, the reactions of pyridine are very much related to temperature conditions. So in this case, if we use the temperature at 200 to 300 degrees centigrade and we use elemental halogen, whereas halogen here is chlorine or bromine, we will get three substituted or 3,5 disubstituted pyridine derivatives. And if the reaction temperature is kept 300 to 500 degrees centigrade, we will get 2 substituted or 2,6 disubstituted pyridine derivative. So these were some electrophilic substitution reactions of pyridine. Now we see nucleophilic substitution reactions. As we have talked earlier, that pyridine undergoes nucleophilic substitution reactions more readily as compared to electrophilic substitution reactions, and generally nitrogen, oxygen, sulfur and carbon based nucleophiles are used for these reactions. And for example, we see a general reaction for this. So nucleophile would attack here and we will get this one, and nucleophilic substitution reaction takes place via addition elimination process. First nucleophile was added and then X was eliminated, and we get in general 2 substituted product. X can be hydrogen or halogen, whereas for nucleophiles we have wide range. For example, NH2 negative, OH negative, or alkoxides, RS negative, alkyl lithiums, and amines, as well as ALH4 negative. So these are different nucleophiles which can be used to carry out nucleophilic substitution reactions, and this is the general mechanism how it takes place. Nucleophilic substitution reaction of pyridine can also take place via benzyne intermediate. For example, if we have 3-chloropyridine and we treat it with KNH2 in liquid ammonia, as a result we will get this heterocyclic intermediate, and if it is treated with ammonia we can have attack here as well as here, and in general both the isomers are formed. This one is formed in approximately 25% and this one is formed in approximately 45% quantity. In comparison to pyridine, N-alkyl pyridinium salts are more reactive to nucleophilic substitution reactions. For example, nucleophilic substitution reactions of N-alkyl pyridinium ions take place more fast as compared to pyridine. Here again we will have this. And we will get nucleophilic substitution reaction. Now we study the Chichi-Babin reaction, amination reaction, which was first studied for pyridine. In this reaction, pyridine is treated with sodium amide and it is converted into 2-aminopyridine. And here is the mechanism. This negative attacks here and it gets here, and as a result we get this. This one, and this is also coordinated with sodium, and in the next step minus sodium hydride. Sodium hydride is eliminated and we will get this one. Now sodium hydride, which was eliminated, takes this proton and we get deprotonated amine, and in the end, upon treatment with water and as well as sodium hydroxide, we get 2-aminopyridine. Students, this is all for today's lecture, and I hope you have understood all of these, and remaining lectures will be uploaded soon. And if you have any question or query, please leave them in comment box. Thanks.